Hello students, today we are going to discuss an important question of stereoisomerism from coordination compounds. So let us read the question. Write the sum of geometrical isomers in platinum alanine complex and the stereoisomers of platinum glycinate complex. So we are having two complexes of platinum, of which we need to find out the geometrical isomers for the first complex, and for the second complex we need to find out stereoisomers. So stereoisomers include geometrical as well as optical. Okay, so this is the thing. For the second complex we need to find out geometrical as well as optical, and for the first complex we need to find only the geometrical isomers. Okay, let us do the question. So this is the first complex. The structure of the first complex looks like this manner, and if you look at that, there are two donor sites there, like one is of nitrogen. One is of nitrogen, one is of nitrogen, and one is of oxygen. So there are two donor sites there, and we are just denoting it as A and B. So this is a bidentate ligand. So likewise, how many ligand is there? Two ligands are there. So two donor site is there, and total two ligands are there. So 4 is the total coordination number of this complex, and since platinum it is in the 5D series, 4 coordination number means the geometry is square planar geometry, and the shape will be of square planar shape. Okay, next let us see how we can find out the geometrical isomerism for this particular complex. So we will draw the detailed structure of this complex. Okay, this is the structure we can make. So the first structure what I made is, I made NH2 and O minus 180 degree opposite to each other. I will just discuss about the second structure, just wait a minute. So the first structure I made NH2 and O minus 180 degree opposite to each other, right? Here also NH2 and O minus 180 degree opposite to each other, and this is a square planar complex. Okay, now let us see this first. This carbon, if you check, this hybridization of this carbon is sp3. Any doubt is there? The hybridization of this carbon is sp3. Obviously, this CH3 will go up, this hydrogen will go down. Similarly, this carbon also, if we check, this is sp3 as well. So likewise, this CH3 can go up, and this hydrogen can go down. Since these two CH3 and CH3 are on the same side, if you imagine, if you think all this entire thing is on the same plane. If you think all these things, are on the same plane, this CH3 will go up, this hydrogen will go down, this CH3 will go up, this hydrogen will go down. Are you getting me? All this red colored part, assume that they are in the plane of the paper, and this CH3 is coming towards us, right? So this we can call it as this will be the cis form. Similarly, we can make another change here. This CH3 can even go downward, right? If you consider a plane like this, okay, if you consider a plane like this, this CH3 can go up and one CH3 can go down, right? So this will be the second form, that means the trans form of this thing, correct? So we have got two geometrical isomers. Okay, so we have got two geometrical isomers when we have assumed NH2 and O minus 180 degree opposite to each other. When we have made like this, we have found that there is one sp3 carbon is there which is having a CH3 substituent is there. So we can have a different spatial arrangement for this CH3 carbon. So we have made, in the both side we have made CH3 on the same side, we got one cis form, and we have just changed CH3 downward, we have got to the trans form. Any doubt is there? Now what will be the next structure we can make out of this complex? Yes, we can make NH2 and NH2 opposite to each other. So here we made NH2 and O minus opposite to each other. In this both case we made NH2 and O minus opposite to each other. So what will be the next possibility? We can make NH2 and NH2 180 degree opposite to each other. So that is the next figure. NH2, so if you look at here, NH2 and NH2 are 180 degree opposite to each other. Here also NH2 and NH2 is 180 degree opposite to each other. Now, like in the previous case, if you draw a plane like this, if you take a plane, because it is a square planar complex, right? If you take a plane like this, if you take a plane like this, okay, so this CH3, since this carbon is sp3, this carbon is also sp3, okay, so this CH3 can go up, this CH3 can also go up. Since this both CH3 are on the same side, we will take it as cis. Similarly, if you do for the second case, we are getting a plane, because it is a square planar complex, right? So this we are getting, and this CH3 is on the above side. So this is sp3 carbon, this is also sp3 carbon, right? This is also sp3 carbon. Here if you check CH3 and CH3, they are opposite to each other, like one is above the plane, one is below the plane. So this is nothing but a trans. Okay, so from the previous case we have got a 1, 2, now we have got a 3, 4. So total geometrical isomers we made for this particular complex, we have got 4 geometrical isomers we made. Okay, how we made? I will just revise once again. First I made NH2 and O minus 180 degree opposite to each other, and with respect to these two carbons, that means this CH3 connected carbons, we made 2 different configurations, like CH3 and CH3 are on the same side, CH3 and CH3 are on the opposite side. So what is the next possibility I made? I made NH2 and NH2 180 degree opposite to each other, that is this structure. NH2 and NH2 180 degree opposite to each other, I made 2 structures, and the CH3 part, because of this carbon is sp3, we can make this CH3 above the plane, below the plane as well. So if we make both the CH3 on the same side, we are getting cis. If both CH3 we are keeping opposite to each other, we are getting trans. Likewise we are getting 4 geometrical isomers, we are getting 4 GI for this particular complex. We are getting total 4 geometrical isomers for the first complex. Okay, let us move to the second complex. So the second complex is given platinum glycinate complex. Okay, let us see what it is given. It is nitrogen and oxygen is given. Obviously this is also a bidentate ligand, because it is connected with 2 donor site, right? Because 2 donor site is there, obviously it is a bidentate ligand. Likewise, how many bidentate ligand is there? How many? 3 bidentate ligands are there, which is having 2 donor site. So the total coordination number is 6. So the geometry of the complex is octahedral complex, and the shape will looks like this manner. Okay, octahedral complex looks like this manner. So I will be just denoting this complex by A and B. The rest of the part CH2 and CO, we will be just drawing with a curve. Any doubt is there? No, we will just move. These are the 2 things we can make out of the spatial arrangement of this particular complex. Okay, so this is of metal AB thrice system. So whatever you draw, this will be the repetition of either of these 2. Okay, so how to check this? The first structure I made, A and B opposite to each other, A and B opposite to each other, A and B opposite to each other. So everything is opposite to each other, means A and B, they are opposite to each other for the first case. So while let us see for the second case, What will happen for the second case? Second case, I made A and A opposite to each other. B and B I made opposite to each other. A and B opposite to each other. So here majority of the case A and A is opposite to each other. That means A and A is opposite to each other. B and B is opposite to each other. But for the first case, there is no such cases like A and A is nowhere it is opposite to each other. B and B is also nowhere opposite to each other. So obviously the second structure is different from that of the first one. So if you draw any other third structure, that will be the repetition of either of these two. That is for sure. You can try it out. Okay. So let us discuss about the optical isomerism for the first case. So optical isomerism, we need to check is there any plane of symmetry. If there is plane of symmetry is there, we will say that it is optically inactive. So we will just check if there any plane of symmetry is there. Let us consider one plane like through this rectangular shape. Okay. Are we able to divide this compound into two equal halves? No, right? Because the first part, this A and B part, which is on the back side of the rectangle, while this B and A, which is on the front side of the rectangle. So obviously it does not have any plane of symmetry, or we will write it as optically. It is optically active. It is optically active. So since it is optically active, we can tell that it will exist as a enantiomers, right? So it will be, there will be a mirror image as well will be there. As non-superimposable mirror image as well will be there for this particular complex. So total there will be 2 will be coming, because it is optically active, so it will be existing as its mirror image as well. There will be 2 forms for this particular compound. One is the given compound and other will be the it's a mirror image. I'll just remove this thing, you may get confused. Okay. Other will be the mirror image of this. Okay. So if you draw, if we keep a mirror like this, whatever the compound we are getting, that will be the second form. Okay, are you getting me? Since this compound does not have any plane of symmetry, it is optically active. Okay, let us see for the next second case. Let us see for the second case. Second case also, if you check, if you draw a plane like this, we are not able to get a plane of symmetry, right? It is not dividing it into equal 2 halves. You may be thinking that there are A and A is coming down to each other, but the problem, if you see the problem, if you check the problem here, this A and B is on the back side of that rectangle, while this A and B is on the front side of the rectangle. So even if you draw a plane of symmetry, which is this blue color, it is not dividing this compound equally into two halves. Why? Because this AB is coming behind this AB is the back side, and this means this AB is the front side and this AB is the back side. So you cannot divide this into 2 equal halves. Okay, so this is also optically inactive, optically active. Okay, so this is optically active. So this will be also existing as a mirror image is also there. Its mirror image is there. So total is coming it as 2. So the total stereoisomerism, if you speak, I told in the beginning, geometrical as well as optical. Geometrical, if you speak, this A and A is opposite to each other, right? So we will call it as trans. So this part, definitely this will be of cis. So this cis form can be of 2 types, that means optically active 2 forms will be there. Similarly, trans form will be of 2 forms will be there, because it is optically active. So the total number is 2 plus 2, 4 we are getting for this particular complex. So we are getting 4. Okay, so what is the answer of this complex? For the first complex, we got 4. Okay, for the second complex, now we got it as 4. So what is the answer? Answer is 4 plus 4, which is equal to 8. So the answer, the sum of these two complex, whatever the question is given, sum of geometrical isomers in the first complex and the stereoisomers in the second complex is 8. Okay, so if you have any doubt, let me know. I will be happy to help you. There may be some difficulty for you to understand the stereochemistry. Don't hesitate to ask. If you have any doubt, I will be happy to help you. Thank you. Study well.